All right, this video is going to be a quick overview of the entire lesson. We will get through all of the examples, and I'd advise you if that you're following along with this video and you want extra practice, that you would be pausing, do the examples by yourself, and then catch up or see how I did it to compare answers. So we're talking about inequality symbols. It's important to know that we can read inequalities in two different directions. This is read x is less than 6. This is read x is less than 6. This is read from left to right that we're used to in English. But in other cultures, other languages, you read from right to left. So they'd read x is less than 6. We also can have a less than or equal to symbol. Having a little line underneath means equal to. So this is less than equal to and less than equal to in both directions. We can have greater than. So we're looking at numbers greater than 5 for our unknown value. And we can do it as well in the opposite direction. And we can have a greater than and equal to in both directions. It's important to also know that we have combinations. We could have x is greater than 3 but less than or equal to 7. Okay, this is read either this way, or we could have 7, x being between 7 and 3. It's important to note that the 3 and the 7 cannot exchange places because it's impossible for a number to be less than 3 but greater than 7. So this would be the two ways. Now when we're graphing inequalities, just erase this. X is less than 6 either way. We're going to do it on a one-dimensional number line. It's like it shows all the numbers that x could be. And x could be any number that is underneath 6. And it's going to get really, really close to 6. So we could include numbers like 5.5, 5.7, 5.9, 5.99, 5.999. That's still a number that's less than 6. But it's tough to see where we stop if we're using this line. So just to kind of emphasize that we are going to go up to but not include 6, we'll use an open circle. We'll also use an arrow to denote that we have all values that are less than 6. Okay? If we have x greater than 5, either way, you read it. Again, you would have numbers including 5.0001. All these numbers up to but not including 5. And we will have an open circle there as well. If I have those compound inequalities, x is greater than 3 but less than 7, we would, we also, if I had a line underneath it, less than or equal to and greater than or equal to, means we would include 6 and include 5. So we would make that open circle a closed circle. So open circles to mean stop right at that point, all values up to but not including, and then with the equals including. So just to kind of show that here, we have 3 and 7 on the number line, making sure they're in the correct order. We're going to go up to but not include 3, but we will include 7, and all the values in between will count. Now we can use bracket notation for these inequalities. So let's just do it right here, just so we can see them all at the same time. So some bracket notation. Now notice all the values that x could be. X could be anything that is a negative value, a very large negative value, any value less than 6. Well, if I am including 6, I'm going to use these squared off brackets. Squared off brackets means include. Open brackets means do not include. So all of my values for x will include 6. That's my biggest number, so I have the right bracket here. And I'm going to include all values all the way to negative infinity. Now, do we include or not include negative infinity? Well, we actually not include it. We do not include it because infinity is more of a concept rather than a value that can be included. So we will always use a bracket with infinity. Okay, so this one, we're starting at 5 and we're going to positive infinity. Our bracket notation would look like this. And if I have one that's included and one that's not included, for this guy, I would not include 3, but I would include 7. Now, it's important, if this was just an open circle, this would just be an open bracket. If this was just an open circle, this would just be an open bracket. Okay, but everything else would stay the same. So write the inequality in 2 different ways, one of which could be graphing. So we have this interval notation using x's. I can change this into bracket notation as well as graphing. Open circle, closed circle. Here, I can say we are going to be greater than or equal to -2 and less than 3, and also graph. Here we have x, all x's that are bigger than 1. Notice I just have just that, open circle, and if I were to use the bracket notation, I would not include 1 and go into infinity. Here I'd have x's that are less than or equal to -2. I would start at -infinity and include -2. Great. A couple more. X is less than 7. Don't include 7, but everything up to 7. -infinity to 7. Here, 1 to 2. X's have to be between, but don't include 1 and 2. Now, let's talk about solving linear equalities. Okay? Or let's just talk about what algebraically we can do to an inequality. Well, most of our algebra rules still apply. Really, they all apply. It's just there's one little caveat. There's one little thing we have to be careful of. Okay? So if I wanted to add a certain value, totally capable of adding something, and the true statement here, we started with 1 less than 3. Well, 5 is less than 7. That remains true. I could multiply, and this goes for subtraction. Subtraction, same thing, it's just addition's tricky friend. We can multiply. So let's say I multiplied by 2. Well, it's still a true statement. 10 is still less than 14. And that goes with division. Division is just multiplication's tricky friend. Except for one thing. And we have to be careful with multiplication and division. If I multiplied by a negative, let's just take -1. Okay, watch what happens. This turns into -10, and this turns into -14. Well, in terms of like the quantity, if we looked at the absolute value or the distance from 0, 14 is like bigger, you know, like, right? 14 is bigger than 10. But in terms of less than and greater than, once you get into the negative numbers, things change. The greater the negative number, the less the value is. The further away it's 0, the lesser the value is. If I kept this inequality symbol the same, this would be false. So, what do I have to do to make it true? I actually have to flip my symbol. Okay? So that's the one thing we have to be careful of. All the other algebra rules apply. If you multiply or divide by a negative, you must flip your inequality symbol. All right? So, solving linear equalities. Let's just walk ourselves through this guy. I'll do it step by step. Sorry that the answers are already visible. We have 3x minus 2 is greater than 13. Well, same algebra rules apply. I'm going to solve this inequality just like I solved equalities. I'm going to first get rid of the 2. I'm going to try to isolate the x, get rid of the stuff being added first. We're undoing the order of operations. We have 3x is greater than 15. I then will divide or multiply, either divide by 3 or multiply by 1/3. Since I'm dividing by a positive or multiplying by a positive, things stay still, everything is good, you don't have to change any symbols. If x is greater than 5, you can talk about not including 5 going to infinity, or you can talk about graphing, and my solutions for x are all solutions that are bigger than 5. So that means back in this original, starting at 5.00001, we are going to have true statements. As long as you plug in any x bigger than 5 into this original inequality, we will have a true statement, and that's what we're looking for. Okay, these are just simple. Maybe you want to subtract. Maybe you want to divide by 1/3. It's the same as multiplying by 3. All simple, all easy. 2 to infinity. Don't include. Negative infinity to 6. Include. Oh, sorry, this is x is greater than or equal to, so this is 6 to infinity. Including. Never including infinity. Here's a couple more. We want to look at these because this is an example of when we'd have to possibly flip things. So I have negative 2x plus 1. I subtract 1. I have negative 2x is less than or equal to 12. Here's when I can divide by negative 2 or multiply by negative a half. When I do that, I must flip my symbol. Okay? We could check. Our values must be bigger than negative 6. Let's check a value like 0. If I plug in 0, do I get a true statement? 1 is less than 13. That's true. If I plug in 1, I get negative 2 plus 1. That's negative 1. That's less than 13. That's true. So this checks out. It's always good to check your answers bigger than or equal to negative 6. Let's maybe do graphically this time. Here's a good question. We could do things a couple different ways. If you'd like to maybe always have your x's on one side, you can add negative 5x to both sides. But you can already see that if you add negative 5x to this side, you'd have a negative value that you'd have to get rid of by dividing, and you'd have to flip a symbol. Maybe you are one of those people that forgets to flip symbols. So maybe instead of doing that, you add a negative x to this side. If negative 4 is greater than or equal to 4x plus 12, you then can subtract 12. You get negative 16 is greater than or equal to 4x. You divide by positive 4, multiply by 1/4. You get negative 4. Now notice I divided by a positive, even though this is a negative value. Since I divided by a positive, I do not flip my symbol. Okay, it's only when you divide by a negative. I did not divide by a negative. This stays still. Now, just be careful. The x is on the right side. Just read it correctly. My values, x, have to be less than or equal to negative 4. So if I have negative 4, my values x have to be less than or equal to that negative 4. Okay, or from negative infinity to negative 4, including negative 4. A couple more. We can distribute. I would probably change this to plus and negative. Same rules apply. If you have terms on the same side, I'd advise you to combine. Subtract the 5x's from both sides, or add negative 5x's. I have a negative 3 left over. I have an x plus 3. I then can subtract the 3. When I subtract the 3, I get negative 6. X is bigger than negative 6. Notice, I did that on purpose. I like to have positive values for x's. If I subtracted 6x, watch what I'd have to do. If I subtract 6x from both sides, this would be a negative 1x plus negative 3, which is less than 3. Then this would be negative x. I'd have to add 3 to both sides, is less than 6. Now I divide by negative 1, symbol flips. Okay, so just be careful when doing these problems. Make sure you just, however you're doing it correctly. Same thing. I could either move the 4x or move the 3x. I'm going to move the 3x. I like to keep things positive when I deal with inequalities. Or really just anytime I'm solving an equation. I like to keep things positive if I can. I wrote down 1x. I did not have to write down 1x. It's just an x. X is bigger than 4. Bringing us to these two situations. Kind of rewrote it so that it's different. Okay. But let's see what happens. So I have 4x plus 1 is greater than or equal to 4x plus 3. I'm going to go ahead and distribute. 4x plus 4 is greater than or equal to 4x plus 12. And here's 7 plus 3x plus 3 is less than or equal to 3x plus 15. All right. So let's deal with this one first. If I subtracted 4x from both sides, or add negative 4x, do it from both entire sides. I have 4 is greater than or equal to 12. Did I make a mistake? Well, make sure you understand that x's are gone. I've subtracted all of the x's, so there's no more x's left over. So this is correct what I did. But I have 4 is greater than or equal to 12. I know that's just not true. 4 is not bigger than 12. What does that mean? That means there's no value for x that I could have placed in here to get me a true statement so that the right side here is less than the left side, and the left side is greater than the right side. So this is an example using an inequality where there are no solutions. Let's see what happens over here. I have 3x plus 10 is less than or equal to 3x plus 15. And I have 10 is less than or equal to 15. Well, that's after I subtract the 3x. Well, this is a true statement. Okay, 15 is bigger than 10 or equal to 10. And I can do any type of manipulation of 10 and 15 if I wanted to, but boom, we're done. The x's are gone. This is a true statement. What does this mean? X can be anything. Any number, any fraction, any decimal, we call anything all reals in math. Okay, let's do a couple more as we have some fractions here. I'd advise you to pause, do the problems, and then come back and check your work. What I would advise here is to multiply both sides by 6, because it'd be a common, well, two things to do. You can either multiply by 6 or multiply both sides by the other's denominator, like 2 over 2 and 3 over 3. Multiply by 6 because I'll have 6 times. I'll pull out that 1 that divide by 3, make it a 1/3 times 2x plus 1. That way I know 6 divided by 3 can be 2. Over here we have 6 divided by 2 is 3. So this would be 3x minus 2, or x minus 2 times 3 on the other side. I would distribute. 4x plus 2 is greater than 3x minus 6. Subtract 3x, I have an x. Subtract the 2, I have minus 8. That's the same as adding negative 2, so this is minus 8. X is bigger than negative 8. This guy, I can just get rid of the 5 right away, multiply both sides by 5. In this situation, you cannot undo this 1 that's being added because of this division. It's really kind of captured things. If you'd like to, you could write this as 1/5 times 3x plus 1. And if you'd like to distribute this 1/5 in and make it 3/5 x plus 1/5, it's the same as dividing every term by the 5. You can do that and then subtract the 1/5. Best thing to do when you have a fraction like this is to just multiply both sides to get rid of this 5. Now I have 3x plus 1 is greater than or equal to 10. Now the 1 is freed up to be moved. I can add the opposite. And then divide or multiply by the reciprocal. Okay, a couple more. I'd probably multiply both sides by 6 again here. This is really the same as the problem above, but a little bit different. When I multiply by the 6, this is 3x plus 3. It just gets rid of the fractions so that when I distribute, I don't have so many fractions to work with. Just good advice, best practices here. This is plus and negative, so this is plus and negative. Add negative 2x's to both sides. I have 1x. subtract 9 from both sides, or add negative 9, and that's negative 17. This guy, let's say you want to work with fractions, go ahead. Add negative 3/10 to both sides. Maybe you have a calculator and you don't mind. You have 2/5 x is less than. I have to turn this into 5/10. 5/10 minus 3/10 or plus negative 3/10 is 2/10, which is 1/5. So this is just 1/5. Solve for x, you can multiply by the reciprocal or multiply by 5 divided by 2. Either way it works. X is less than 1/2. That's 5/10, or the 5's cancel. It's important when you see multiple inequalities, like these guys, that you do two things. Okay? Two ways to tackle multiple inequalities where we have, manipulations of x. You could either split this into two different inequalities and just solve both of them normally. Add negative 2x, negative 2 to both sides. You get negative 5 is greater than x. And here, this is x is less than 3. And then you can combine them back again. Negative 5 is less than x, which is less than 3. And you have negative 5 and 3. Open circle, all the values in between. Or if you feel brave and daring, just go ahead and work with both equations at the same time. Just the manipulations need to be done everywhere. If you'd add negative 2 to the middle, just do it to both outsides to get you negative 4 is less than 3x, which is less than or equal to 9. Then I would divide everything by 3. Negative 4/3 is less than x, which is less than or equal to 3. Okay? Both decent ways to do things. Make sure we include the 3. When we are doing stated problems with inequalities, just make sure you can read this as a greater than, or this is x is at least. This is less than or at most. Okay. Product of 3 times a number is no greater than 12. So product of 3 times a number is no greater than 12. So I guess that less than could also be no greater. Let's solve that. 3 consecutive odd numbers, so that's a number plus 2 to get our second odd number, plus a number plus 4 to get our third odd number, is to be added up to be greater than 30, but less than 75. Okay? We have this compound inequality. We can add things up. And again, we can split this into 2 or just work all at once. Maybe I'll add negative 6 everywhere. This turns into 24. This turns into 69. And then divide by 3. I get 8, and I get 23. Okay? So I wonder, 23, 25, 27. That gives us 75. So 23 is the start of the biggest number. You could go to 27 as the largest number because we're having x and our biggest number is thing. So it's just I wouldn't worry too much about it, but if you think about it, the largest number that you can have in your 3 consecutive odd numbers is 27. With the final left to go, Leah needs to finish a grade between an 85 and 88 to keep in good standing with her parents. She has an 85 for the first 9 weeks. So 85, 45%. 88 for a second 9 weeks. That's good. What is the range of scores on her final to keep her in the range? So for her final, we need to be between or equal to an 85 and an 88. Okay, this is just an example of setting up an inequality. You could almost set it up as like an equation. Just understand you need to be between the two numbers. That works. I would go ahead and do this calculation, subtract from both sides. Might as well do it. A calculator. So we had 85 times 0.45 plus 88 times 0.4. This number is 73.45. 0.1x, or less than or equal to and greater than or equal to. So I'm going to subtract that 73.45 from the 88. I get 14.55. I made a mistake. This should be a 0.45. I don't know why I did that. That's 77.85. You can kind of see when your numbers look a little bit off, like, I probably made a mistake somewhere. So this is 77.85. Subtract that from 88, you get 10.15. So strange. And from the other one, you get 7.15. Divide both sides by 0.1, we end up just moving the decimal place over one place. And it turns out, as long as you get above a 71.5, you're going to be between an 85 and an 88. You're good. So tough to move your overall average up. All right, we'll finish there. So those are your inequalities.